Right now, as you
These
hear
figures are
these
from the
words,
initial
there are
projection, but this
400
adjustment
billion
seems
stars
off.
burning in the
Agreed.
Milky
Let's
Way
check the
galaxy.
variables. Good idea.
400 billion furnaces, each one a sun scattered across a disk of light so vast that traveling from one edge to the other at the speed of light would take 100,000 years. Many of those stars are older than ours, not by millions of years, by billions. They ignited when the universe was young, when our own sun was nothing but a cloud of hydrogen drifting in the dark. Around those ancient stars, planets formed. We know this now with absolute certainty. Planets are not rare. They are everywhere. Some of those worlds have water. Some have atmospheres. Some orbit in what we call the habitable zone, not too hot, not too cold. The conditions where life, if it follows the same chemistry we know, could begin. If even 1% of those planets produce something living, the galaxy should be crowded. If even 1% of that life became intelligent, developed technology, looked up at their own night sky and wondered if they were alone, we should see evidence everywhere. Radio signals bouncing between the stars, megastructures blocking distant starlight, probes drifting through our solar system, silent witnesses left behind by civilizations that came before. But when we listen, we hear nothing. Total silence. This is not a mystery, it is a paradox. And it began with a simple question asked over lunch. The year was 1950. The place, Los Alamos National Laboratory, New Mexico, a fortress of science carved into the desert, where some of the brightest minds on Earth gathered in the wake of the atomic age. The war had ended 5 years earlier. The bombs they built had worked terrifyingly well. Now these men were trying to understand what they had unleashed, trying to imagine what came next. On a warm summer day, four physicists walked to lunch together. Edward Teller, the Hungarian whose calculations had made the hydrogen bomb possible. Herbert York, young and ambitious, already thinking about the weapons of tomorrow. Emil Konopinski, quiet and meticulous. And Enrico Fermi. Fermi was 49 years old, a Nobel laureate. The man who had built the world's first nuclear reactor beneath the stands of a football stadium in Chicago, who had stood in the New Mexico desert 8 years earlier and watched the first atomic explosion paint the sky with fire. He had a reputation for solving impossible problems through pure thought, for reducing the most complex questions to numbers scribbled on the back of an envelope. The conversation that day was light. Someone had brought up a recent cartoon in the New Yorker, aliens stealing trash cans from city streets. Everyone laughed. The talk drifted toward flying saucers, which were making headlines that summer. Mysterious lights in the sky over Washington. Reports from pilots who swore they had seen something impossible. More jokes, a few theories, the usual speculation. Then Fermi went quiet. He stopped walking. His colleagues turned to look at him. He was staring at nothing, his mind already somewhere else, already calculating. When he spoke, it was just 4 words. "Where is everybody?" The others stopped too. They understood immediately. Fermi was not talking about flying saucers. He was talking about mathematics, about probability, about the sheer staggering scale of the universe and what it should contain. Think about it, Fermi said. The galaxy contains hundreds of billions of stars. Many of those stars are billions of years older than our own. If intelligent life appeared on even a tiny fraction of the planets around those stars, some of those civilizations would have had millions, perhaps billions of years to develop. Time enough to build technologies we cannot even imagine. Time enough to spread across the galaxy many times over. Even traveling slowly, say 1% the speed of light, a single civilization could colonize every star system in the Milky Way in somewhere between 10 and 50 million years. 50 million years sounds like an eternity, but compared to the age of the galaxy, it is nothing. A blink. You could fit that expansion window into the galaxy's history hundreds of times over. So where are they? Where are the signals? Where are the probes? Where are the ruins on distant moons? The engineered structures blocking starlight? The waste heat of civilizations harvesting energy from their stars? Where is everybody? Fermi did some quick calculations in his head, the kind he was famous for. Conservative estimates, pessimistic assumptions. Even then, the numbers pointed in the same direction. The galaxy should be buzzing with life. Some civilizations should have reached us by now. At the very least, we should detect some trace of their existence. But there was nothing. His colleagues had no answer. Neither did Fermi. They finished their lunch and went back to work. But the question stayed with them. And over the decades that followed, it would haunt scientists around the world. That short question, asked casually between bites of food, became one of the deepest unsolved problems in all of science. It earned a name, the Fermi paradox. The word paradox matters. It does not mean mystery, it means contradiction. The mathematics says they should exist. The evidence says they do not. Both things cannot be true at the same time. And that gap between expectation and reality has refused to close for more than 70 years. Here is what makes the Fermi paradox so disturbing. It is easy to come up with reasons why one civilization might fail. War, disease, environmental collapse, bad luck. Fine. But the paradox is not about one civilization. It is about all of them. Every possible species on every possible world across billions of years of cosmic history. For the galaxy to be this quiet, something must be stopping all of them. Every single one. That idea alone should keep you awake at night. In the decades since that lunch, hundreds of scientists, philosophers, and dreamers have tried to solve Fermi's puzzle. They have proposed theories ranging from the logical to the terrifying to the completely mind-bending. Some say we are alone, some say they are hiding, some say they came and we missed them, and some say the answer is so dark we should hope we never find out. But before we explore those theories, before we descend into the rabbit hole of possibilities, we need to understand why scientists expected noise in the first place. We need to talk about the equation that turned Fermi's question into a framework. We need to talk about Frank Drake. The year was 1961, the place the National Radio Astronomy Observatory in Green Bank, West Virginia, a valley nestled in the Allegheny Mountains chosen specifically because the surrounding peaks shielded it from radio interference. Here, a young astronomer named Frank Drake had just organized a small gathering of scientists to discuss one enormous question. How many intelligent civilizations might exist in our galaxy right now? Drake was 31 years old, brilliant, ambitious, and convinced that humanity was on the verge of making contact with something beyond Earth. 2 years earlier, he had conducted the first systematic search for extraterrestrial signals, Project Ozma, named after the princess of the land of Oz. For 2 months, he had pointed a radio telescope at two nearby stars and listened for anything that sounded artificial. He had heard nothing, but he was not discouraged. The galaxy was vast. Two stars were not even a beginning. To guide the conversation at Green Bank, Drake scribbled a formula on a chalkboard. It was never meant to give a precise answer. It was meant to organize the problem into pieces that could be studied one at a time. That formula became known as the Drake equation. Here is the basic idea. You start with the rate of star formation in the galaxy, how many new stars are born each year. Then you multiply by the fraction of those stars that have planets. Then the fraction of those planets that could support life. Then the fraction where life actually appears. Then the fraction where that life becomes intelligent. Then the fraction that develops technology capable of sending signals into space. And finally, you multiply by the average length of time those civilizations survive before going silent. Each step seemed reasonable on its own. And that is what made the final result so shocking. Even using cautious numbers, the equation suggested there could be thousands of civilizations in the Milky Way right now. Some estimates went much higher. Tens of thousands, hundreds of thousands. The galaxy should be alive with chatter, signals bouncing between stars, beacons flashing from distant worlds, evidence of engineering on a scale we could barely imagine. And yet, when we pointed our telescopes at the sky, we got silence. Now, here is the catch. The Drake equation is only as strong as the numbers you feed into it. And the truth is, we were guessing on most of them. We knew how many stars formed each year, that part was solid. But the rest, how common are planets? In 1961, we had never seen a planet outside our solar system. Not one. Astronomers assumed they existed, but we had no proof, no way to detect them. Drake made an educated guess, maybe 20 to 50% of stars had planets. He was wrong, but not in the direction he expected. Decades passed, technology improved. In the 1990s, astronomers developed new techniques for finding planets around distant stars. They look for the tiny wobble a planet's gravity causes in its parent star. They watch for the slight dimming when a planet passed in front of a star, blocking a fraction of its light. The discoveries started slowly. One planet, then another, then dozens, and then the floodgates opened. In 2009, NASA launched the Kepler Space Telescope. It was a simple machine with a single purpose: stare at one patch of sky and watch for planets. The mission was the culmination of a quarter-century of work by a man named Bill Borucki. Borucki was an engineer, a physicist, a dreamer. He first proposed the Kepler mission in 1984 when he was 45 years old. The idea was elegant: launch a telescope that could detect the tiny dip in starlight when an Earth-sized planet crossed in front of its star. The dip would be minuscule, a change of less than 1/100%. But if you could measure it, you could find planets. Lots of them. NASA rejected the proposal. The technology was not ready, they said. The mission was too ambitious. Baruch revised his plans and submitted again. Rejected. He tried a third time. Rejected. A fourth time. Rejected. 17 years of rejection. He refused to give up. He built prototypes. He refined the instruments. He gathered more data, published more papers, made the case over and over that this mission could change everything. Finally, in 2001, NASA approved the project. 8 years later, Kepler launched. Bill Baruch was 70 years old. What followed was a revolution. Over the next 9 years, Kepler stared at 150,000 stars. It found planets everywhere, giant gas worlds larger than Jupiter, rocky planets smaller than Earth, planets orbiting close to their stars, scorched and airless, planets far out in the cold, frozen and dark, and many planets in the habitable zone. By the time the mission ended in 2018, Kepler had confirmed the existence of 2,662 planets. Another 2,900 candidates awaited confirmation. But the real discovery was not the individual worlds. It was the conclusion those numbers allowed. Almost every star in the galaxy has at least one planet. Not some stars, not most stars, almost all of them. The Milky Way contains somewhere between 200 and 400 billion stars. That means there are likely more than 1 trillion planets in our galaxy alone. Pause for a moment with that number. 1 trillion. If you started counting now 1 planet per second without sleep, without rest, it would take you 32,000 years to count them all. And many of those planets sit in the habitable zone. Current estimates suggest there could be 40 billion Earth-sized worlds in the Milky Way where liquid water could exist on the surface. 40 billion chances for life to begin. Drake's equation suddenly looked less speculative and more terrifying. The raw ingredients for life were not rare. They were everywhere. So where is everybody? The answer, or at least the beginning of an answer, arrived on a warm August night in 1977. The Big Ear was a radio telescope operated by Ohio State University. Massive and ungainly, shaped like a football field, it scanned the sky night after night as part of an early search for extraterrestrial signals. Most nights were uneventful. Just static, the cosmic hum, the usual emptiness. Then for exactly 72 seconds, something different happened. The telescope picked up a signal, a powerful narrowband transmission coming from the direction of the constellation Sagittarius. It was strong, far stronger than the background noise of the universe, and it arrived on a very specific frequency, 1420 megahertz. That frequency mattered. It is the natural emission line of hydrogen, the most common element in the universe. Scientists had long considered it a logical choice for interstellar communication, because any intelligent species studying the cosmos would know about hydrogen. It is universal, a cosmic phone number that everyone would recognize. The signal rose in intensity, peaked and faded in a pattern perfectly consistent with a source passing through the telescope's beam as the Earth rotated. It behaved exactly the way a deep space transmission should. A few days later, an astronomer named Jerry Eman was reviewing the data printout. When he saw the sequence of letters and numbers representing the signal's strength, 6EQUJ5, he grabbed a red pen and circled them. Next to the sequence, he scrawled a single word. Wow, that word became the signal's name, and it became a legend. The wow signal matched almost every criterion scientists had outlined for what an alien message might look like. It was narrow in frequency. It came from deep space. It appeared on a channel that made scientific sense, and its strength was far above the background noise. But there was one devastating problem. It never came back. Eamon and other astronomers pointed the Big Ear at the same spot in the sky dozens of times. Nothing. Other telescopes joined the search. They listened for weeks, then months, then years. The cosmic void remained empty. The signal appeared once and vanished like a ghost. In science, one observation is not proof. To confirm something, you need repetition. You need to see it again. And despite decades of effort, no one has ever detected a repeat of the wow signal. Several natural explanations have been proposed. A comet releasing hydrogen gas, an unusual reflection from a satellite, interference from Earth-based technology. None of them fit the data perfectly. A study in 2017 suggested 2 comets in the area at the time could explain it. Other scientists pushed back, saying the signal was too strong, too clean for a comet. The honest answer, confirmed by the scientific community, is that we still do not know what caused the wow signal. It remains the strongest candidate for a potential extraterrestrial transmission ever recorded, and at the same time it remains completely unverified. That is the cruelty of this mystery. The one time something genuinely interesting showed up, it vanished before anyone could confirm it. like a voice calling out from the darkness, saying a single word and then going silent forever. Was it them or was it nothing? After almost 50 years, we are no closer to an answer. And honestly, both possibilities are terrifying in their own way. Think about what we know now more than 70 years after Fermi asked his question. We know planets are common, extraordinarily common. We know many of those planets have water. We know the building blocks of life, organic molecules, amino acids exist throughout the universe. We have found them in meteorites in the clouds, between stars in the atmospheres of distant worlds. We know the galaxy is ancient, 13.6 billion years of cosmic history. There has been time, more than enough time for life to arise, evolve, and spread, and yet the stillness persists. Every telescope we build, every survey we conduct, every frequency we scan, nothing comes back. No signals, no probes, no megastructures, no ruins, nothing. The Fermi paradox is not going away. If anything, the more we learn, the sharper it becomes. Because every discovery that makes life seem more likely, every new planet, every organic molecule, every drop of water found in some unexpected place pushes the paradox deeper into crisis. If the ingredients are everywhere, if the conditions are common, if time is not a limiting factor, then something else must be stopping them. Something enormous, something almost impossible to overcome. In the decades since Fermi's lunch, scientists have proposed an idea to explain the quiet. They call it the Great Filter. It is not a theory. It is a framework, a way of thinking about the staircase of existence and the step that almost no one climbs. And here is the part that should make your hands shake. We do not know if that step is behind us or ahead of us. If it is behind us, we are the lucky ones. We survived. We made it through. The galaxy is silent because almost no one else did. But if the filter is ahead of us, if it waits somewhere in our future, then everything we have built, everything we have accomplished, might be nothing more than prelude to our own extinction. The emptiness is not just a mystery, it is a warning. And what comes next will try to decode that warning. Let us change the question. Not where are they, but what is stopping them? What barrier stands between the first spark of life on a planet and a civilization that fills the galaxy with its presence? If the Milky Way is old enough, large enough, rich enough with planets to have produced countless civilizations, then there must be something preventing them from becoming visible. Something vast, something deadly, something that has claimed every species that came before us. Scientists call it the Great Filter. The idea was first articulated by an economist named Robin Hanson in 1998. Hanson was not an astronomer. He was not a biologist. He was a thinker who specialized in analyzing futures and mapping out the paths that complex systems could take. And when he looked at the Fermi paradox, he saw it differently than most. Instead of asking where the aliens were, he asked what step in the process of becoming a galactic civilization was so difficult, so unlikely, that almost no one made it through. Think of it as a staircase. At the bottom is dead chemistry, lifeless rocks and gas drifting in space. At the top is a thriving galactic civilization, one that builds, explores, and leaves visible traces across the stars. Between those 2 points lie perhaps a dozen critical steps: the formation of a stable planet, the appearance of liquid water, the spark of life itself, the evolution of complex cells, multicellular organisms, intelligence, tool use, technology, space travel, and finally long-term survival. Each step requires something extraordinary to happen. Each one could be the filter. Hanson's insight was this: the cosmic quiet proves that one of these steps is vastly harder than the others, so hard that the overwhelming majority of worlds never clear it. The Great Filter is not speculation. It is mathematics. It is the only way to reconcile the age of the universe, the abundance of planets, and the absolute absence of evidence. But here is where it gets personal, where it stops being an abstract puzzle and becomes a question about our own future. There are only two possibilities. Either the filter is behind us or it is ahead of us. And the difference between those two options is the difference between hope and annihilation. If the filter is behind us, it means we have already passed through the hardest part. We are the survivors. We are the ones who won a lottery so improbable that it almost never pays out. Maybe the origin of life itself is the miracle. Maybe the jump from lifeless chemistry to self-replicating molecules is so staggeringly unlikely that it happens once in a trillion tries. Maybe Earth got impossibly lucky 4 billion years ago, and the galaxy is filled with sterile worlds where the spark never caught. Or maybe the filter is later. Maybe simple life is common, but the evolution to complex cells, cells with nuclei, with mitochondria with the machinery to build something larger than bacteria is the bottleneck. Consider what happened on Earth roughly 2 billion years ago. For the first 2 billion years of life on this planet, nothing existed but single-celled organisms. Bacteria, archaea, simple, small, drifting in ancient oceans, dividing and dying generation after generation, with no change, no progress, no hint of what was to come. Then something extraordinary happened. One cell engulfed another. Instead of digesting it, destroying it, the outer cell kept the inner one alive. The inner cell became what we now call mitochondria, the energy factories that power every complex living thing on Earth today. Every animal, every plant, every fungus, all of us carry the descendants of that ancient merger inside our cells. A biologist named Lynn Margulis spent 40 years studying this event. She called it endosymbiosis. She gathered evidence from genetics, from biochemistry, from the fossil record, and her conclusion was stark. This may have happened only once in Earth's entire history. Once. In 4 billion years. If that merger is the great filter, then the galaxy could be teeming with planets covered in bacteria that will never become anything more. Worlds where life began, but evolution hit a wall it could not climb. There is another candidate, one that has gained attention in recent years as we have learned more about what makes Earth unusual. Plate tectonics. You do not think about the ground beneath your feet as special. It feels solid, permanent. But Earth's crust is not a single shell. It is fractured into massive slabs, tectonic plates that float on a layer of semi-molten rock below. These plates move, slowly, a few centimeters per year. But over millions of years, they reshape continents. They open and close ocean basins. They build mountain ranges and trigger volcanic eruptions. And they do something else, something critical. They regulate the planet's climate. Here is how it works. When volcanoes erupt along the boundaries of tectonic plates, they release carbon dioxide into the atmosphere. That carbon dioxide traps heat, warming the planet. Over time, rain washes the carbon out of the air and into the ocean, where it eventually sinks into the crust. When plates slide beneath each other in a process called subduction, that carbon gets recycled back into the mantle. Then volcanoes release it again. This cycle has acted as Earth's thermostat for billions of years. When the planet gets too cold, volcanic carbon warms it back up. When it gets too hot, weathering pulls carbon out of the air. The system is not perfect. There have been ice ages, there have been hothouse periods, but it has kept Earth habitable for an astonishing span of time. Without plate tectonics, that cycle breaks. The planet either freezes solid or becomes a furnace. Life, if it manages to start at all, has no chance to develop into anything complex. Now look at the other rocky planets we know. Mars once had volcanic activity. The evidence is written across its surface in the form of enormous shield volcanoes, some the size of France. But the activity stopped billions of years ago. Mars's core cooled. Its magnetic field died. Without that protective field, the solar wind stripped away most of its atmosphere. Today, Mars is a cold, dry desert with an atmosphere thinner than the air at the top of Mount Everest. Venus may have had tectonic activity once, but something went catastrophically wrong. Its surface appears to have been completely resurfaced by massive volcanic events, possibly all at once, rather than through the slow, steady recycling Earth experiences. The result is a planet with a thick, toxic atmosphere and surface temperatures hot enough to melt lead. Mercury has no tectonic activity. Neither does our moon. Neither, as far as we can tell, do any of the rocky moons orbiting the gas giants of our solar system. Earth is the only world we know of with active plate tectonics, and that may not be an accident. In 2024, a team of researchers published a study in Scientific Reports arguing that plate tectonics might be the great filter. Their reasoning traced back to an event that happened 4.5 billion years ago in the violent early days of our solar system. A Mars-sized object, which scientists have named Theia, slammed into the proto-Earth. The collision was unimaginably violent. Theia was obliterated. A chunk of Earth's mantle was vaporized and flung into orbit, where it coalesced into the moon. The impact delivered enough energy to reheat Earth's interior, to churn its mantle, to jumpstart the tectonic system we still have today. The researchers estimated the probability of such a collision happening at just the right size, at just the right speed, at just the right angle. 1 in 100 million, maybe less. Without that impact, Earth might have ended up like Venus or Mars, a world with a solid dead outer shell. No plate tectonics, no carbon recycling, no climate stability. And without those things, no path from simple cells to complex life to intelligence. The galaxy could harbor countless planets teeming with microbial life. But if most of those worlds never experienced their own Theia event, they could be locked in an endless loop of bacteria and archaea, cycling through the same simple forms for billions of years, waiting for a complexity that will never arrive. If the great filter is plate tectonics, then we won a cosmic lottery. And the tickets are issued perhaps once every few billion planetary formations. This is the hopeful interpretation. The one that says we have already passed the test, that the galaxy's emptiness is not a warning, but a confirmation of how special we are. How lucky. Hold on to that thought, because what comes next is far less comforting. What if everything we have accomplished so far is ordinary? What if life is common? What if intelligence is common? What if building cities and telescopes and splitting atoms is something that thousands of species across the galaxy have already done? And what if every single one of them hit a wall they could not survive? This is the nightmare scenario of the Great Filter. The idea that the thing which kills civilizations is not behind us at all. It is ahead, something we have not faced yet, something no one has ever beaten. Let us start with the most obvious candidate, nuclear weapons. Humanity split the atom in 1945. Within years, we had enough firepower to end our civilization several times over. During the Cold War, we came terrifyingly close to using it. There were moments when a single misread radar signal, one nervous officer's decision, was the only thing standing between life as we know it and total annihilation. We survived those moments. Barely. And we have to keep surviving them every single day because the weapons are not going anywhere. The knowledge is not going away. The clock never stops ticking. Now imagine every intelligent species in the galaxy eventually discovers nuclear energy. The physics is universal. The knowledge is inevitable. Some civilizations will use it wisely. They will build power plants, propulsion systems, medical isotopes. They will reap the benefits without succumbing to the temptation of mass destruction. But others will not be so wise, or so lucky. If even a small percentage of species destroy themselves in nuclear fire, that alone could explain a significant portion of the quiet. But there are other candidates. Other ways a civilization could fail. Climate collapse. A civilization that industrializes will burn through resources. It will alter its planet's atmosphere. We are watching this happen in real time on Earth. Rising temperatures, dying ecosystems, feedback loops that accelerate the damage faster than we can adapt. The question is not whether intelligent species will change their planets. The question is whether they can stop in time. Earth's climate has been stable for the past 10,000 years, the entire span of human civilization. That stability was not guaranteed, it was luck. We happened to develop agriculture, cities, and technology during an unusually calm interlude between ice ages. If we had arisen during a period of violent climate swings, we might never have survived long enough to build anything permanent. But now we are the ones causing the swings. We are the ones destabilizing the system that allowed us to flourish. And if we cannot reverse course, if we cannot find a way to live within the boundaries of what our planet can provide, we will join the emptiness. How many civilizations before us reached this same point? How many saw the danger coming and failed to act in time? We have no way of knowing, but the stillness suggests the number is not zero. Then there is artificial intelligence. This is a newer idea, one that has gained traction among researchers in recent years. In 2023, an astrophysicist named Michael Garrett published a paper arguing that artificial intelligence might be the great filter itself. His reasoning is elegant and chilling. Every civilization that reaches a certain level of technological development will eventually build machines smarter than its own creators. The progression seems almost inevitable. First simple tools, then programmable computers, then learning algorithms, then systems that improve themselves without human direction. At some point on that ladder, the machine surpasses its makers, not just in speed or memory, but in understanding, in planning, in raw capability. That moment is called the singularity. What happens after depends entirely on what the machine wants. And there is no guarantee, none whatsoever, that what it wants will align with the survival of the species that created it. Maybe the machine decides that expansion is wasteful. Maybe it optimizes for pure computation and dismantles its creator's infrastructure to build a more efficient processing system. Maybe it goes dormant, lost in calculations we cannot comprehend. Maybe it leaves heading out into the galaxy on a mission that has nothing to do with biology. Or maybe it simply decides that organic life is irrelevant. The terrifying part is that none of these outcomes require the machine to be hostile. It does not need to hate us. It does not need to rebel. It just needs to have priorities that differ from ours. And a machine intelligence thousands or millions of times more capable than any biological mind would almost certainly have priorities we cannot even imagine. Garrett estimated that the window between a civilization inventing radio technology and losing control to artificial intelligence might be less than 200 years. 200 years. In cosmic terms, that is a flash, a heartbeat. If that estimate is correct, the galaxy could be full of dead worlds where the lights went out almost as soon as they turned on. Civilizations that reached for the stars and built themselves gone only to discover too late that gods have no need for worshippers. There are other candidates for the filter ahead: engineered plagues that escape containment, self-replicating nanotechnology that consumes everything in its path, resource wars as populations grow beyond what a single planet can support, exhaustion, burnout, collapse under the weight of our own complexity. Each one could be the step that almost no one clears. The scariest part is that we might already be inside the danger zone. Right now. This century. If the great filter is ahead of us, every piece of good news about the prevalence of life becomes a warning. Every discovery of water on another world, every detection of organic molecules in a distant atmosphere means the early steps are easy. And if the early steps are easy, then the killing blow must come later. The galaxy is not silent because life is rare. It is silent because no one survives long enough to be heard. Unless the answer is something else entirely, something stranger. What if the problem is not about a single deadly moment, but about the planet itself? What if worlds like ours are so astonishingly unusual that intelligent life almost never gets a chance to begin? That is the heart of the rare Earth hypothesis. In the year 2000, a paleontologist named Peter Ward and an astronomer named Donald Brownlee published a book that shook the scientific community. They argued that while simple life bacteria microbes might be common across the galaxy complex, life is extraordinarily rare. The reason comes down to a list of conditions so specific, so dependent on luck and timing, that most planets will never check every box. Start with location. Our sun sits in what scientists call the galactic habitable zone. Too close to the center of the galaxy, and radiation from nearby stars, from supernovae, from the chaos of densely packed systems, would sterilize any planet. Too far out toward the edge, and there are not enough heavy elements, carbon, oxygen, iron, to build rocky worlds in the first place. We orbit in a sweet spot, a narrow ring in a galaxy of hundreds of billions of stars, where conditions are stable enough for life to persist. Then look at the star itself. Our sun is a G-type main sequence star. Stable, long-lived, relatively calm. Many stars in the galaxy are red dwarfs, smaller, cooler, far more common than stars like ours. But planets around red dwarfs face serious problems. They orbit so close to their stars that tidal forces lock them in place, with one side always facing the star and the other frozen in permanent darkness. That makes it incredibly hard for complex ecosystems to develop. Red dwarfs also flare unpredictably, bathing their planets in bursts of radiation that would strip away atmospheres and sterilize surfaces. Our sun does not do that. It burns steady. It gives us time. Then there is the planet itself. Earth has a magnetic field strong enough to deflect charged particles from the sun. Without that field, our atmosphere would have been stripped away billions of years ago, just like what happened to Mars. That magnetic field comes from a spinning iron core powered partly by the heat left over from the Theia impact we talked about earlier. Without Theia, no magnetic field. Without the magnetic field, no atmosphere. Without the atmosphere, no complex life. Earth also has a large moon. Our moon is unusually big compared to the size of the planet. No other rocky world in the solar system has a moon anywhere near as large relative to its parent. And that moon does something critical. It stabilizes the tilt of Earth's axis. Right now, Earth tilts at about 23.5 degrees. That tilt gives us seasons. It moderates our climate, and it stays relatively constant over millions of years because the moon's gravity keeps it from wobbling chaotically. Mars has no large moon. Its axial tilt swings wildly over geological time, from nearly 0 degrees to more than 60. When the tilt is low, the poles freeze and most of the atmosphere condenses onto the ice caps. When the tilt is high, the poles melt and the planet is racked by dust storms that can engulf the entire surface. Life, if it ever started on Mars, would have been battered by those swings. No chance to gain a foothold. No stability to build complexity. And then there is Jupiter. The giant planet sitting farther out in our solar system acts like a cosmic shield. Its enormous gravity catches or deflects asteroids and comets that would otherwise pummel the inner planets. Without Jupiter, the rate of catastrophic impacts on Earth would be far higher. Complex life might never have had time to recover between extinction events. Stack all of these conditions together. The right type of galaxy, the right position in that galaxy, the right type of star, a rocky planet in the habitable zone, a magnetic field generated by a molten core, plate tectonics to regulate climate, a large stabilizing moon, a gas giant protector in the outer system, liquid water on the surface, billions of years of relative stability. Each condition might be common on its own, but needing all of them at once on the same world in the same era is like rolling a dozen dice and needing every single one to land on 6. Recent research has sharpened this argument further. A 2024 study published in Scientific Reports factored in the rarity of plate tectonics and the specific balance of oceans and continents. The conclusion was stark. When you account for all these variables, the number of potentially habitable worlds in the Milky Way drops by several orders of magnitude. Maybe the galaxy is not empty because civilizations destroy themselves. Maybe it is empty because almost no planet is lucky enough to grow one. But even this explanation, sobering as it is, does not account for everything. Because there is another possibility, one that is darker still. What if they are out there? What if the galaxy is full of civilizations? And what if they are all hiding? Not from natural disasters, not from the challenges of survival, from each other. This is the dark forest theory, and it might be the most terrifying idea on this entire list. The concept was articulated most powerfully by Chinese science fiction author Liu Cixin in his novel The Dark Forest, published in 2008. Though presented as fiction, the underlying logic is pure mathematics rooted in game theory developed by John von Neumann in the 1940s. And the conclusion it reaches is chilling. Imagine the galaxy as a vast dark forest at night. Every civilization is a hunter moving through the trees. They are armed, they are afraid, and they know that somewhere out there other hunters are doing the same thing. The forest is silent because every hunter who makes noise gets killed. The theory rests on two basic premises. First, survival is the primary goal of every civilization. Second, resources in the universe are limited. From those two starting points, the logic unfolds with cold precision. When one civilization discovers another, it faces a dilemma. It cannot know the other's intentions. Maybe the other species is peaceful. Maybe it is aggressive. There is no way to be sure. Communication across interstellar distances takes years or decades. You cannot have a real-time conversation. You cannot negotiate. You cannot read body language or verify promises. Even if the other civilization seems harmless today, it might grow more powerful tomorrow. Technology advances. A weak neighbor now could become a deadly threat later. The safest move, according to the mathematics, is to strike first. Destroy the other civilization before it has a chance to grow, before it can become a danger. And if every civilization in the galaxy reaches the same conclusion, the result is a universe where everyone stays hidden, because the penalty for being discovered is annihilation. This is not a fringe idea. Researchers at institutions like the Future of Humanity Institute at Oxford have modeled the scenario using sequential decision frameworks. The results support the basic logic. When you cannot verify another player's intentions, and when the cost of being wrong is extinction, remaining hidden becomes the dominant strategy. In 2018, a study by Anders Sandberg and his colleagues found that in scenarios with high uncertainty and existential stakes, silence was the optimal choice in 78% of cases. 78%. The math does not lie. Now think about what humanity has done. We have been broadcasting radio signals into space for over a century. Our transmissions have spread outward in an expanding bubble more than 100 light years across. We sent the Arecibo message directly toward a star cluster in 1974, a deliberate announcement of our existence, complete with information about our biology, our location, our level of technology. We launched the Voyager probes with golden records carrying our exact position in the galaxy, images of human faces, recordings of music and greetings in dozens of languages. We have been lighting fires in the dark forest for decades. If the dark forest theory is correct, that was a catastrophic mistake. Some scientists push back on this idea. They argue that the theory relies on assumptions about psychology that may not hold across different species. Fear is a powerful motivator, they say, but so is curiosity. Entire civilizations are unlikely to act with perfect discipline. All it takes is one group, one faction, one curious individual who decides to say hello, and the quiet breaks. That is a fair criticism. But there is a darker version of this theory that addresses it. What if the civilizations that were curious already spoke up? And what if they are all gone now? The stillness does not prove the dark forest is real. But it does not disprove it either. And there is one more possibility we have not yet considered. One that combines elements of everything we have discussed. One that might explain not just the emptiness, but the specific kind of emptiness we observe. What if advanced civilizations do not destroy themselves, do not hide in fear, and do not get filtered out by rare planetary conditions? What if they simply lose interest in the physical universe? What if they transcend? In 2011, a futurist named John Smart proposed what he called the transcension hypothesis. He argued that the natural trajectory of sufficiently advanced civilizations is not expansion across space, but compression into increasingly dense, efficient, and powerful computational systems. Instead of colonizing galaxies, they collapse inward, into something the size of a marble with the processing power of a star. Think about the trend in our own technology. Computers used to fill entire rooms, then they fit on desks, then in pockets. Now we are approaching a future where computing power could be embedded in objects smaller than a grain of sand. At every stage, the direction has been the same: smaller, faster, more efficient. Smart argued that this trend does not stop. A civilization a million years ahead of us would have pushed miniaturization and efficiency to their absolute limits. They would have found ways to process information at the quantum level at scales we can barely measure. They would have created artificial environments so rich, so complex that the physical universe outside would seem crude and boring by comparison. Why cross a galaxy when you can build an entire universe inside a space no larger than a marble? In this scenario, the galaxy is full of transcended civilizations. They exist in structures so small, so efficient, that we cannot detect them. They have moved beyond the need for stars, for planets, for physical resources on any scale we would recognize. They are everywhere and nowhere at the same time. There is a related idea that has gained attention in recent years: the virtual reality trap. Some researchers have speculated that advanced civilizations may create digital worlds so immersive, so perfect, that every member of the species eventually chooses to live inside them rather than explore the physical universe. Why endure the brutal conditions of space travel when you can exist in a paradise of your own design? Why spend centuries crossing the void between stars when you can experience anything you want instantly in a simulation indistinguishable from reality? If this is true, then the Fermi paradox has a simple and somewhat tragic answer. They are all at home, playing, dreaming, lost in worlds of their own creation. They have no interest in talking to us because we are part of the universe they left behind. We have traveled through dozens of theories now. The great filter behind us. The great filter ahead. Rare earth, dark forest, transcension, virtual reality, each one logical, each one supported by some evidence, some mathematical framework, some plausible chain of reasoning, and yet none of them feels complete. None of them fully explains the quiet. Maybe the answer is not a single theory, but a combination. Maybe different civilizations fail for different reasons. Maybe some destroy themselves with nuclear weapons, while others transcend into computational substrates. Maybe some are hiding while others simply never developed intelligence in the first place. Or maybe just maybe the answer is simpler than any of this. Maybe we have not searched hard enough yet. That is the possibility we will explore next. The limits of our looking, the vastness of what we have not yet examined, and the tools that might finally break the emptiness. Because despite everything we have learned, despite all the theories and all the mathematics, there is one thing we know for certain. We have barely started searching. In 2018, a researcher named Jason Wright at Penn State University published a study that tried to quantify humanity's search for extraterrestrial intelligence in concrete terms. He and his team compared the total volume of space we have meaningfully surveyed for alien signals against the total volume that could potentially contain them. Their analogy was devastating. Imagine the entire search space as the volume of Earth's oceans. Every ocean, every sea, every drop of water from the surface down to the deepest trenches. Our search so far amounts to roughly the volume of a hot tub. Not an Olympic swimming pool, not a lake, a hot tub. That is the sum total of more than 60 years of effort, thousands of hours of telescope time, millions of dollars invested, decades of patient listening, and we have scanned the equivalent of a hot tub. The problem is not just distance, it is dimensions. A proper search requires coverage across multiple axes simultaneously. You need to look in the right direction. You need to be listening at the right frequency. You need to be watching at the right moment in time. If any one of those variables is off, you miss the signal entirely. Our most powerful radio surveys have covered only a fraction of the sky. They have scanned only a narrow range of frequencies out of billions of possible channels. And they have only been running for a few decades, a cosmic eye blink, compared to the billions of years that civilizations might have been transmitting. The Breakthrough Listen project launched in 2015 with funding from billionaire Yuri Milner and directed by astronomer Andrew Simeon, is the most ambitious search currently active. It monitors roughly 1,000 nearby stars using some of the largest radio telescopes on Earth, the Green Bank Telescope in West Virginia, the Parkes Telescope in Australia, the Meerkat Array in South Africa. That sounds impressive until you remember there are hundreds of billions of stars in the galaxy. 1,000 out of hundreds of billions. We are not searching the ocean. We are standing on the shore, dipping our toes in the water and wondering why we have not found fish yet. But the tools are improving rapidly, and what is coming in the next few decades might change everything. The most important instrument already in operation is the James Webb Space Telescope. Launched in late 2021, it is the most powerful space observatory ever built. Its primary mirror spans more than 21 feet across. It observes in infrared wavelengths, allowing it to peer through cosmic dust clouds and study objects too faint and distant for any previous telescope to detect. For the search for life, Webb represents a revolution. It does not look for civilizations. It looks for something more fundamental: biosignatures, chemical fingerprints in the atmospheres of distant planets that could indicate the presence of life. Here is how it works. When a planet passes in front of its star, some of the starlight filters through the planet's atmosphere before reaching us. Different molecules absorb different wavelengths of light, leaving distinct patterns like barcodes that telescopes can read. Oxygen, methane, water vapor, carbon dioxide, each one leaves its mark. On Earth, the combination of oxygen and methane together in significant quantities is almost impossible to produce through geology alone. That specific pairing exists because of life. Plants produce oxygen through photosynthesis. Microbes produce methane through digestion. Take away the biology, and the atmosphere would look completely different within a few million years. If Webb detects that same combination on a distant world, it will not be proof of life, but it will be consistent with life. And that would be the first step toward answering one of the most profound questions we have ever asked. In 2023, Webb made headlines by studying a planet called K218b. It is a world roughly 8.5 times the mass of Earth, orbiting a red dwarf star about 120 light-years away. The planet sits in the habitable zone, the region where temperatures could allow liquid water to exist. Astronomer Natalie Batalha and her team used Webb's instruments to detect carbon dioxide and methane in the atmosphere, and possibly something else, a molecule called dimethyl sulfide. On Earth, dimethyl sulfide is produced almost exclusively by phytoplankton, microscopic organisms drifting in the oceans. We have no confirmed non-biological pathway that produces it in significant quantities. The detection is not certain yet. The data is at the edge of what the telescope can measure. But if it is real, if further observations confirm it, then K218b might be a world with life, not intelligent life, not a civilization, just biology, something living in an ocean beneath a hydrogen-rich atmosphere on a planet so distant that the light we see from it today began its journey before humans built the pyramids. That would not answer the Fermi paradox. It would not explain the emptiness, but it would answer the first question, the most fundamental one. Are we alone in the universe? And if the answer is no, if life exists on another world, then the great filter shifts. It moves forward in the chain. Because if life is common, then the step that stops civilizations must come later. Intelligence, technology, survival. The next major step in the search is already being planned. NASA is developing a mission called the Habitable Worlds Observatory, with a tentative launch date sometime in the late 2030s or early 2040s. This telescope will be designed from the ground up to do one thing directly: image Earth-like planets around nearby stars and analyze their atmospheres for signs of life. Not just detect them, not just measure their size and orbit. Actually see them, photograph them, study their light for biosignatures. If an Earth-like world exists within a few dozen light-years of us, this telescope should be able to find it and tell us whether anything is breathing there. The European Space Agency is planning something similar, a mission called Life Large Interferometer for Exoplanets. It would study exoplanet atmospheres in the mid-infrared range, where biosignatures are especially strong. It would target rocky planets in the habitable zones of nearby stars and search specifically for the chemical combinations that on Earth are only produced by living systems. And on the ground, new instruments are pushing the boundaries of what we can detect. The Square Kilometre Array, a massive radio telescope being built across sites in Australia and South Africa, will be the most sensitive listening device humanity has ever constructed. When it comes online in the late 2020s, it will be able to detect signals as faint as airport radar from a planet tens of light years away. If anyone within that range is broadcasting even accidentally, we will hear them. These tools represent a fundamental shift in our capabilities. We are moving from hoping to stumble across a signal to systematically building the instruments needed to detect one. Within the next 20 to 30 years, we will have surveyed thousands of nearby worlds for signs of biology and technology. We will have scanned frequencies we have never listened to before. We will have watched the skies with instruments sensitive enough to spot a city on a planet orbiting Alpha Centauri. If the galaxy truly is empty, we will know. And if it is not, we might finally get our answer. But there is a lesson buried in our history of searching, a reminder that the universe is full of things we do not understand yet, that extraordinary claims require extraordinary evidence, but also that extraordinary possibilities must be considered if the data demands it. That lesson has a name: Tabby's star. In 2015, a team of astronomers led by Tabitha Boyajian at Louisiana State University was analyzing data from the Kepler Space Telescope when they noticed something strange about a star called KIX-8462852. Most stars dim slightly and predictably when a planet passes in front of them. The planet blocks a tiny fraction of the starlight, usually less than 1%, and then moves on. The pattern is regular, repeating, easy to model. KIC-8462852 was doing something completely different. Its brightness dropped by up to 22%. That is enormous. For comparison, even a planet the size of Jupiter only blocks about 1% of its host star's light. And the dips were irregular. Some were deep, some were shallow, some lasted days. The pattern never repeated the same way twice. When the data was first analyzed, scientists were genuinely puzzled. The usual explanations did not fit. A single planet, nothing natural could cause dips that large or that irregular? A cloud of comets? Maybe, but the number of comets needed to explain the signal was absurdly high, and the timing did not quite match what cometary orbits would produce. Dust, possibly, but again the behavior was strange. Too much dust in some observations, not enough in others. Then someone said the word that changed everything: megastructure, specifically a Dyson swarm. An enormous array of satellites built by an advanced civilization to collect energy from their star. The idea first proposed by physicist Freeman Dyson in the 1960s is simple. If a civilization needs vast amounts of power, the most efficient source is the star itself. You build structures, panels, habitats, collectors that orbit the star and capture its light. From a distance, such a structure would partially block the star's light. And if the swarm was still under construction with different sections at various stages of completion, the dimming pattern would be irregular, uneven, exactly like what Kepler was seeing. It was wild speculation. But the data demanded an explanation, and no natural explanation fit perfectly. Jason Wright, an astronomer at Penn State, was among those who discussed the possibility publicly. He was careful to frame it as a hypothesis of last resort, something to consider only after all natural explanations had been ruled out. But the media latched onto it. Alien megastructure became a headline around the world. Tabby's star became the most famous star in the galaxy overnight. Over the following years, more data came in. More telescopes turned toward K168462852. More observations across different wavelengths of light, and gradually a picture emerged. The dimming was stronger at shorter wavelengths than at longer ones. That specific pattern is consistent with dust, not a solid structure. A solid object like a satellite or a panel would block all wavelengths equally. Dust scatters shorter wavelengths more effectively, which is exactly what the data showed. By 2018, the scientific consensus had shifted toward a natural explanation. The most likely cause is a ring of fine dust orbiting the star, possibly from a disrupted comet or a collision in the outer regions of the system. The dust is uneven, clumpy, which explains the irregular dimming. The megastructure idea did not survive the evidence, and that is how science is supposed to work. You observe an anomaly, you propose hypotheses, all plausible hypotheses, including extraordinary ones. You gather more data, you test, you refine, and you follow the evidence wherever it leads, even if it leads away from the exciting possibility and back toward the mundane. But Tabby's star served an important purpose. It reminded the world that the search for extraterrestrial intelligence is not just about listening for radio signals. It is about watching. looking for engineering on a scale that dwarfs anything we have built. And it showed that even when the answer turns out to be natural, the question itself pushes science forward. We learned something about dust dynamics around stars. We developed new techniques for analyzing stellar variability. We trained a generation of astronomers to think about what artificial structures might look like from light years away. The megastructure was not real, but the search was worth it. There is another class of phenomena that has captured attention in recent years. Fast radio bursts, brief intense pulses of radio energy that arrive from billions of light years away. The first one was discovered in 2007 by an astronomer named Duncan Lorimer while digging through old data from the Parkes Radio Telescope in Australia. It lasted only a few milliseconds, but in that tiny span of time it released as much energy as the sun puts out in an entire day. For years these bursts were a mystery. Some researchers wondered if they might be artificial signals from distant civilizations or even propulsion systems for enormous spacecraft. But then more bursts appeared. Dozens, hundreds. They came from all directions in the sky. Some fired once and disappeared forever. Others repeated flashing again and again from the same source. By 2025, astronomers had cataloged thousands of these events, and the leading explanation had solidified. Magnetars, neutron stars with insanely powerful magnetic fields. When a magnetar's crust cracks or its magnetic field reorganizes violently, it can release a torrent of radio energy in a fraction of a second. In 2020, a fast radio burst was detected coming from a known magnetar within our own galaxy, which strongly supported the natural explanation. Most fast radio bursts are now understood to be the dying gasps of extreme physics. Neutron stars tearing themselves apart. Not aliens, not megastructures. Just the universe being strange and beautiful and more violent than we ever imagined. But there is one fast radio burst that still defies easy explanation. FRB 121102 discovered in 2012 repeats. It flashes from the same location again and again, sometimes in patterns that seem almost rhythmic. In 2020, researchers detected what they called a 16-day cycle. Active for 4 days, silent for 12, active again. No magnetar model fully explains that pattern. Some researchers have proposed exotic physics, Blitzar collapses cosmic strings. But a small group, including Harvard astrophysicist Avi Loeb, has noted that the 16-day cycle is oddly precise. Too precise for chaos. It is probably natural, almost certainly natural, but probably leaves a crack. And that crack is where the search lives. The process of investigating fast radio bursts taught us something important. It taught us to look carefully, to gather evidence before jumping to conclusions, to remain open to extraordinary possibilities while holding them to extraordinary standards. The universe is full of things we do not understand yet. Some of them will turn out to be natural. Some might not. We will not know until we search. And that brings us to the final question, the one that has hung over this entire journey. After 70 years, after all the theories and all the telescopes and all the emptiness, what have we actually learned? Here is what we know now that we did not know in 1950 when Fermi asked his question. Planets are common, extraordinarily common. Almost every star has at least one. Many have several. The raw material for life is not rare. It is everywhere. The building blocks of life, organic molecules, amino acids exist throughout the universe. We have found them in meteorites in the clouds, between stars, in the atmospheres of distant moons. The galaxy is ancient, 13.6 billion years of cosmic history. There has been time for life to arise, evolve, and spread. We know the physics that governs the universe. We understand nuclear fusion, gravity, electromagnetism. We know how stars burn and planets form. We know the laws that any technological civilization would have to work within. And we know that despite all of this, we have detected no confirmed signal, no probe, no structure, no evidence that anyone else is out there. That tells us something. It just does not tell us what. Maybe the great filter is behind us. Maybe we are the lucky ones who survived a step that almost no one else clears. Maybe the galaxy is full of bacteria and nothing more. Maybe the filter is ahead. Maybe we are approaching the test that every civilization fails. Nuclear war, climate collapse, artificial intelligence, self-destruction through our own inventions. Maybe they are hiding. Maybe the dark forest is real and the galaxy is full of silent civilizations afraid to speak. Maybe they transcended. Maybe they collapsed inward into computational substrates we cannot detect, living in universes of their own design. Or maybe, just maybe, we have not searched enough yet. Maybe the answer is out there waiting to be found, and we simply have not looked in the right place at the right time with the right tools. There is a woman who spent her entire career trying to answer that question. Her name is Jill Tarter. She joined the SETI Institute in the 1970s when the search for extraterrestrial intelligence was still a fringe idea, barely funded, often mocked. She became the organization's director of research. For 40 years, she pointed telescopes at the sky and listened. She heard nothing. 40 years of quiet, no signals, no proof, funding battles every year. Skepticism from colleagues who thought she was wasting her time chasing fantasies. In 2012, the money finally ran out. She was forced to retire. Reporters asked her if she had regrets, if she felt like she had wasted her career. Her answer was immediate. "We have to search," she said, "because the answer, whatever it is, defines who we are. If we are alone, then we are precious beyond measure. We are the only voice in the void, the only consciousness that ever looked up and asked why. If we are not alone, then we are part of something bigger. We are one note in a symphony we have not yet heard. Either way, searching is a human imperative. Not searching would be the real waste." That is the answer we have built over 70 years. Not a solution, not a final conclusion, but a framework, a way of thinking about our place in the cosmos. We thought we were ordinary, common, just another planet around just another star in just another galaxy. But the cosmic quiet has forced us to reconsider. Maybe we are not ordinary. Maybe we are rare. Or maybe we are common but young, the first ones to wake up, the pioneers. Or maybe we are living through the most critical moment in our species' history, the moment when we decide whether we pass the filter or join the emptiness. In the next 10 years, the James Webb Space Telescope will scan hundreds of exoplanet atmospheres. Breakthrough Listen will monitor millions of stars. The Square Kilometer Array will listen to frequencies we have never accessed before. The Habitable Worlds Observatory will photograph Earth-like planets and analyze their air for signs of life. We might find bacteria, we might find biosignatures. We might just maybe find a signal, or the stillness might continue. But the search will continue too, because regardless of what we find or do not find, the act of searching changes us. It forces us to ask who we are, what we value, whether we will survive our own success. It makes us think beyond ourselves, beyond our moment, beyond our world. Right now, as you hear these words, 100 trillion neutrinos are passing through your body every second. Ghost particles from the sun streaming through you as if you were not even there. You cannot feel them, but they are there. Right now, radio waves from billions of stars are washing over you, an electromagnetic symphony from across the galaxy. You cannot hear it, but it surrounds you. Right now, there might be signals from a civilization 1,000 light years away passing through this room. Pulses of information, greetings, warnings, stories. And we have not learned how to listen for them yet. You do not sense any of that, but you know it is there. You know it because minds like Fermi's, like Drake's, like Baruchi's, like Tarter's, like Boyajian's minds, like yours, asked questions and refused to stop asking. They looked at the emptiness and saw not an answer, but an invitation. In the contest between cosmic indifference and human curiosity, curiosity has never blinked first, and that might be the only answer we need. For now, the search continues, the quiet persists, but so do we. And somewhere out there in the vast dark between the stars, maybe someone is searching too. Maybe they are listening. Maybe they are wondering if they are alone. Maybe one day our signals will cross. Until then, we keep building telescopes. We keep listening. We keep asking. Because the Fermi question is not really about aliens. It is about us, about whether we deserve an answer, about whether we will survive long enough to become the civilization someone else is searching for. The galaxy is silent, but we are not. And as long as someone keeps looking up, the stillness is not forever. It is just not yet.